Okay, so welcome back. So it's a great pleasure to introduce my colleague, Professor Arijit Samal. So Arijit is actually the first member of our computational biology group. I mean, we are all moonlighting, physicists who kind of pretend to do computational biology. Arijit is the true blue computational biologist here. So Arijit did his PhD in physics, like many of us, with Sanjay Jain at University of Delhi, and went on to do a number of brilliant postdocs with incredible people, including many whom are very well known to people here. So, and then he joined about a decade back, right, Arijit?
I'm sorry?
About a decade back?
Yes.
Yeah. And Arijit's been doing, diverse a range of things, including building up databases of phytochemicals and so on. So among the many things he does is modeling of gene regulatory networks. And so he's very kindly agreed to give us a tutorial on that.
Thanks, Sitabro. It was really a kind introduction. So let me at the outset thank Sitabro, Shakti, Mithun and Fernando for this opportunity to present our work here. I'm very sure that the participants of this workshop are both enjoying and learning a lot. Especially this workshop has been very well planned by the organizers, and I would like to really congratulate them for that. And particularly Sitabro, I want to thank him for actually organizing a range of very high level meetings over the last 22 years in math science. And these meetings have actually shaped a generation of Indian students who have tried or attempted and made forays into the broad area of complex systems. So recently it happened that I was cleaning the room, actually my room in the apartment of my parents in Delhi, and I found this physical photograph of school which Sitabro organized for a month in January of 2006 when I was a second year PhD student, and I attended his meetings amongst various other meetings which actually has shaped my thought process and essentially allowed me to make perhaps the right decisions in my career. So there are some coincidences if you see, and this photo is actually a physical photograph which was sent to all the participants at the end of the meeting by Sitabro, and actually I've scanned the photograph. So you can see some familiar faces here. You can see of course Sitabro, he looks exactly the same 18 years down the line. You can see a familiar speaker in this meeting and that meeting, Professor Shomdatta Sinha, and you can perhaps recognize many speakers and students who have actually gone on to become academicians both in India and abroad. So I made several friendships here which have turned into academic collaborations, again thanks to Sitabro. I wanted to show this picture because it has not been acknowledged that when we look at doing interdisciplinary science in India at this time, that is for the last say 10 years over when I started doing PhD, the situation was very different. Especially after COVID, you can actually Google or go to YouTube and actually get to hear any stalwart in your area, wherever you want to enter. So the information is much more easily accessible. And these meetings, these high-level meetings, and with the line of speakers which Sitabro organized, because it's a lot of selfless service to the community which he did, were really instrumental in shaping our thought process and allowing us to choose the right problems in the area of complex systems. So in short, I wanted to really thank Sitabro for inspiring the generation of Indian students to work in complex systems and its selfless service towards training people in the area of complex systems. Before I go on with this talk, thank you, Sitabro. So actually I don't have a outline slide because I did not know how much I can cover. So actually the broad outline of the set of slides I have in my talk is actually on the blackboard. So I intend to cover a subset of it. The slides will be given away to Shakti, and it's an open Google link so anybody can view it. So I would like to start with a disclaimer that I'm not a developmental biologist. I'm actually can be classified better as a computational /network/data scientist who has primary interest in biological systems. However, since my PhD, which I started in 2003, for about 21 years, I have been broadly interested in a key question, which is to decipher design principles in biological networks, in particular two networks, which is gene regulatory networks and metabolic networks. And in my quest to identify design principles in gene regulatory networks, me and my collaborators and my group members have forayed into the space of Boolean modeling significantly. And I would like to present some of those results tomorrow in the research talk I will be presenting. Shitabro was kind enough to ask me to give a primer or an introduction to Boolean network modeling. It was a big challenge because I hesitate writing things like review papers. I have actually one paper in my career because doing justice to the large body of work which have happened in a space of close to 80 years is not easy. And you have to give the right credit and choose the right topics to present to the students who are perhaps trying to enter the field after, let's say, the proposition by Stuart Kauffman in 1969. So I would like to emphasize that the material that I have decided to present today has been chosen in a very personal sense, and my understanding of what will help you in doing actual research if you intend to do using this framework in the coming years. So what I intend to do is that I want to make in the next few slides a case for studying GRN dynamics, that is dynamics of gene regulatory networks. My work has been simplified by several speakers who have spoken before me in this week already. And then I will, after giving you a historical overview of those who have contributed significantly in this area, I would give you a basics of Boolean modeling of the gene regulatory networks. In particular, I want to touch upon, after introducing the basics of Boolean modeling, how is the dynamics different when we choose between two types of update scheme, say synchronous and asynchronous, which I will introduce later. Then I will come to a pertinent question, which is how do you choose the type of Boolean function which will be used to capture the combinatorial regulation at each node in the network. And I'll touch upon a random choice, threshold choice, or biologically meaningful choices. This topic I am choosing because it is important to understand this, to understand the research talk I will be presenting tomorrow. And if there is time, I will touch upon the important topic of how do we incorporate, quote unquote, the notion of landscape, which has been discussed a lot and is part of the title of this meeting, into this framework of Boolean dynamics. Because the deterministic Boolean dynamics does not particularly allow you to directly impose the landscape constraint which is associated with developmental gene regulatory networks. These may seem not clear to you at this moment, but over the space of this talk I would like to make clear all of these to you as much as possible. So with that, I'll proceed with my talk. So as many speakers have emphasized, cell is the basic unit of life. In multicellular organisms, of course, there are different cell types. All the cell types of a different organism we know have the same genome, but they express different set of genes. Cells are constantly taking decisions as well. Decisions such as to grow or not to grow, to divide or not to divide, that is associated with cell division, to live or not to live, that is they may choose to go and activate the apoptotic pathway, or to be or not to be, that is in the case of the differentiation they may have to decide between which differentiated cell they may take up during the differentiation process. All these cellular decisions are mediated through various networks which are underlying these cells, okay? Especially the gene regulatory and signaling networks. So understanding these decision making processes, we need to understand the dynamics of these networks. To be more explicit, dynamics of the gene regulatory networks is fundamental for several biological processes, which has been emphasized in this workshop already, and in particular in the development. And while we are modeling the dynamics of the gene regulatory network associated with development, we should remember that the different cell types of a multicellular organism have the same genome but express this different sets of genes. And further, the steady state expression patterns associated with the gene regulatory networks correspond to the different cell types. So these are the basic features which any developmental gene regulatory network should capture. Okay. So having made the case for studying the dynamics of gene regulatory networks and incorporating say in developmental gene regulatory networks, the idea of different cell types. There are various modeling frameworks which are available to proceed and study these dynamics. And amongst the simplest and perhaps the most simplest yet elegant mathematical framework which is available to study the dynamics of gene regulatory networks is that proposed by Kaufman. We credit him, but I will mention in the next slide that before Kaufman, others had already thought of the same modeling framework as well, which is the Boolean network framework to study the dynamics of gene regulatory network. So importantly, Kaufman actually pioneered the use of these discrete networks for modeling gene networks, where each gene is thought of as analogous to a electronic switch, which can have two states only, either active or inactive. Importantly, Kaufman viewed the different attractors or steady states of these associated Boolean gene regulatory networks as different cell types of a multicellular organism. So he proposed the framework of random Boolean networks. I will also come down the line why he chose random Boolean networks for studying. In this seminal paper in 1969 in Journal of Theoretical Biology, and also another paper in the same year in Nature. So it is important to mention that in the pre-genome era, that is prior to genome sequencing, there are others also who have made significant contributions to this area. In particular, the work of René Thomas. One of the reasons he doesn't get that much attention is because much of his writing is in French. But Thomas already in 1973 proposed a similar model, a Boolean model for studying the gene regulatory dynamics in this paper in 1973. His student Denis Thyfree, who is very well known, in this article in 2016 mentions that only during the submission process he realized the work of Kaufman and he cited the work. But there was a very important difference in the work of Thomas and Kaufman, in the sense that first of all, the interpretation of Boolean algebra was different in Thomas' work, and in Thomas in general he did not only allow two discrete states associated with a given component but multiple discrete states. For example, a gene can be not expressed at a medium level and expressed at a very high level. And further, he also introduced for the first time the asynchronous update scheme in this 1973 paper. So as we of course credit Kaufman with popularizing and pioneering the work in Boolean networks, it needs to be also mentioned that he was perhaps not the first one to think of discrete modeling of biological systems. So the earliest papers which are cited by Thyfree and others is this paper by McCulloch and Pitts in 1943, where they used discrete modeling to actually study the activity patterns of neurons. And importantly, Kaufman also cites Sugita, who since 1961 and between 61 and 75 wrote a series of papers where he used Boolean framework to model, for example, the dynamics of lac-operon. So, I mean, as you will see a lot in the history of science, usually the person who does the work second actually gets the credit most. So, and also it is important to sustain working in an area to be credited with that work. So, these are some historical facts and giving the right credit to people who have thought of this modeling framework. So, so I hope I have made the case for studying the dynamics of gene regulatory networks, and the second point was amongst the different frameworks which are available to model the dynamics of gene regulatory networks, perhaps the simplest and most elegant in the face of paucity of data even today, Boolean network is an attractive framework to take forward. So in the next few slides, I will try to present you the basics of Boolean modeling with the different building blocks. So Boolean models are very simple. The first building block of a Boolean model are the nodes, which signify genes or transcription factors or signaling molecules, which are the components of the biological system. I will illustrate basics of the Boolean modeling through a simple example with 5 nodes. Here are the 5 nodes which are shown. So each node in a Boolean model can be in 2 states. It's a binary variable, 0 or 1. 1 signifies that the gene may be active and 0 signifies that the gene may be inactive. So of course in reality nothing is 0 and 1. So if you are actually inferring the activity from say expression patterns in microarray or single cell or RNA-seq data, you may have to choose a threshold above which you consider the gene to be active and below which it is inactive. So each node has 2 states, and for a network with n nodes, the number of possible states is 2 to the power n. Okay. So in this case, the state space is basically 32 states because n is 5. Okay. So once you have specified the nodes in the model, and there is only two states possible, this is of course a oversimplification of the reality. The next building block is to decide who regulates whom in the network, and that's captured through the directed network associated with it. Okay. In this 5-node network, there are 16 edges I have shown, and these are directed edges. For example, if you see, x1 is repressing x2, so the edges with blunt heads are signifying inhibition, and edges with the arrowheads are signifying activation. So x3 is activating x2. Okay. So when you build models, typically you may have that information that a gene regulates another gene. This sign may be known or may not be known. Here I am assuming the sign is known. So the second thing is that you have the directed network which tells you who regulates whom in the network. Okay. So that's the second building block. The third building block is you have to decide on the update rule, which basically captures the combinatorial regulation at a given gene. For example, if you see this node x1 in this network example, it's actually regulated by 3 other genes in the network, x3, x4 and x5. x3 is supposed to inhibit x1 while x4 and x5 actually activate it. So now you have to choose a function which captures the combinatorial regulation, that is, for the different possible states of x3, x4 and x5, what is the state of x1. Okay. So this combinatorial regulation in this framework is captured through a Boolean function, and the Boolean function which has been chosen in this example is shown here. That is, the state of x1 at a time t plus 1 is given by naught of the state of x3 at time t. This is a AND symbol which I will specify in the next slide, and x4 and x5. I don't think anybody needs to write because I am going to give away the slides. Okay. So it's an open link, so just please enjoy if you can. So let me just dwell a bit more on the representation of the Boolean functions, which I will be using today and in the next talk as well. So I'll take a particular example where the gene x4, and this is not an example in the example network of five nodes, this is a separate example. So the gene x4 is controlled by 3 genes x1, x2 and x3, and it's controlled by this following logic. So x4 is active if either x3 and x1 are present or x3 and x2 are present. So essentially, if you were to capture what that corresponds in a physical sense in the promoter, you want the presence of both x3 and x1 bound to the promoter to facilitate the RNA polymerase to sit there and go through the transcription process, or have both x3 and x2 bound. So you can represent these Boolean expression which is written here in this form as well. So across the slides which I will present today, I will be interchangeably using for Boolean AND operator either the caret symbol or the product symbol. So actually the product symbol will be omitted here for the AND operator, as you see this. This is x3 and not x2 and not x1. And for the OR logic, I would be using the V symbol and the plus symbol. And for the not symbol, not operator, I will be using the bar over the variable. So actually this Boolean function which is written here in this form can also be represented by this full disjunctive normal form, which is not important today, but it can be further simplified using Boolean algebra to a simplified expression which is shown here. So this Boolean, so of course you can associate an expression with each Boolean function. You can also represent it as what we all understand much better through the truth table. So there are 3 inputs to x4, so that since there are 3 inputs, so the number of possible combinations is 2 to the power 3. So there are 8 combinations. The 8 combinations starting from 000 to 111 are shown in the truth table, and for each combination we have to decide what is the output of the value of the output variable. Okay. So and these are shown here for this Boolean function. An important quantity which I will be using in my talk is what is known as bias. So bias of a function is basically the number of ones in the output column of the truth table. So if you see, there are 8 possibilities in the truth table, and there are 3 ones in the output column. So the bias of this function is 3. In principle, for a function with k inputs, the bias can be between 0 and 2 to the power k. That is, you can have either 0, so all the output entries as 0, or all the output entries as 1. So how bias plays a role, and this will be important in understanding tomorrow's talk when I present some analytical results. Furthermore, You can also view each Boolean function as a Boolean hypercube. So this is the representation of the same function in the Boolean hypercube. So it's a 3 input function. So you can represent the function as a 3 cube. 3 cube will have 8 vertices. In this hypercube, the neighbor of each vertex is essentially another row in the truth table which differs by exactly 1 input. And the vertices are colored in 2 different colors, one corresponding to the output value 0 and one to the output value 1. So here the output value 1 is shown in red and output value 0 in blue. So this expressions or this truth table and the Boolean hypercube represent the same function. Okay. Why I have introduced the Boolean hypercube will be more clear tomorrow when I present the analytical proof for a result that we have found, which can be easily understood by transforming the question in the Boolean hypercube formalism. So this may not be important for today's work. Okay, coming back to the example with 5 nodes. Is there a question? Yeah, Ananta, please.
What if say x1, x2, x3, 3 are there, and now for activating x2 I need x1, then I can't, then for t plus 1 step I can't activate x4 because
please.
I mean I have to, like, if they inputs are interrelated, I mean depends on each other, then I have to first come up with all the inputs to be active, then I need the x4 to be active.
Don't worry. So the update is something which is coming in next 2 slides. You will understand very simply. Okay, don't worry. So this is actually exactly what I will cover in the next slides. Okay, good.
So like in the previous slide, you mentioned there are 3 inputs. That's why it is 2 to the power 3, and we have 8 outputs. So what if, like, for that we make a hypercube? What if we have more than 8?
So there is a 4 cube with 16 vertices, and you can generalize the concept. Okay, it's well worked out in computer science. That's not a problem. I can show you some examples tomorrow. That's not a problem. I just wanted.
I had one doubt. So you talked about x t plus 1 as a function for 3 genes at what they are working at x at time t, but they may have different rates. Different
I'm
time
coming
scales.
to that. I'm coming to that. Just hold on, hang on to the thoughts. Okay. So I'm coming exactly to that. Okay. So please. So just hang on to the questions. I'll cover that. I'm just going through slowly so that you understand the. So I want to first give you the simplest version of the model and then introduce more complexity with it. Okay. So okay. So now that we have associated and this update rule which captures the combinatorial regulation at each node, I have also now specified the at each node update rule which captures the combinatorial regulation. Then we have to go on and study the dynamics. Okay. And when we are going to study the dynamics, we can choose between 2 types of update scheme. I will first take the simplest version, which is the synchronous update scheme, but I will also introduce briefly the asynchronous update scheme. And these are related to the question which was last asked about the timing of different processes. Clearly, the time scales can be different. For example, Boolean models have been constructed where one node is actually a gene, the other could be a non-coding RNA. The time scales of translation and transcription are very different. So we are going to omit such complications, but think in a simplified framework for the first. So in the most simplified update scheme, in the synchronous update, you assume that there is a central clock. That is, all nodes get updated again at a given amount, at a fixed time. Okay, and time is taken as discrete. And I want to show you how this update will work. So we have this example with 5 nodes, and let's start with the initial condition. So there are 32 states, as I said, 2 to the power 5. I will start with one of the initial conditions where all the nodes are in state 0, that is, all nodes are off. And we want to figure out in the next time step t plus 1, what is the state you flow into. So if we evaluate the function which is here at this node, which is x1 t plus 1 is given by this function, you can put in the values of x3, x4 and x5 at time t, which is the previous time. So this is clearly 0, not of 0 is 1, and so these are 0, 0, so it's an AND function, so it will be 0. Okay. So at the next time step, you see that it flows to 0, x1 remains in 0. For x2, if you evaluate this function which is associated with this node, which is not x1 or x3t and not x4t, see, since x1 at this time step is 0, this not of 0 is 1 and this is the OR function that becomes 1, okay. And you can now evaluate each of the nodes, okay, for each of the nodes the update function and figure out where you flow into. So you started with all zeros and you've flown to 0, 1, 1, 0, 0, okay. Now that's what you do in synchronous update, you have a central clock. Now you can ask the next question, so this is the state you go into if you start with all zeros. So next thing to ask is, we can ask if we start with every possible state in the network, which state we go into in the next time step, okay. So there are 32 states and we can figure out which is the next state that we go into, okay. So I have written down here the state transitions for all the 32 states in this network, okay. You can go home and compute them. So if you are worrying about this bracket, what is written in the bracket, so I am going to show a graph here. So I am going to represent the binary string by its integer equivalent for simplicity, okay. So you have integers from 0 to 31 corresponding to the 32 states. So if you see, you started with 0, 0, 0, 0, 0, you went to 0, 1, 1, 0, 0. That's what I showed in the previous slide. And I have worked it out for all the 32 states. Now if I were to view this state transitions as a directed graph, you get this following state transition graph. So if you, for example, started at 0, you went to the state 12. So that's here. But once you are in state 12, that is 0, 1, 1, 0, 0, which is here, in the next time step you remain at state 12, okay. So this 32 states can now viewed as a directed graph, which is the state transition graph. And in the synchronous update scheme, for the example 5 node network I took, you have 5 different disconnected components, and these are the 5 different steady states of the network. And associated with each of these components are also the states from where if you start you are going to flow into that attractor, which are known as the basins of attraction of the attractor. Is that clear? Yeah. I'm sorry? So when you start in 0, next step is to flow to 12.
And then 12 also.
When you flow in 12, you remain in 12, you see. Once you are in 12, you are locked. So that's the steady state, okay. So here in this state transition graph, there are 2 types of attractors I have shown. 4 of the attractors are fixed points, okay. That is, when you reach that state, you will remain locked in that state. There is a 5th attractor here, which is more like a cycle, a 2 cycle. So once you reach 3, you go to 31, you go back then from 31 to 3 and you keep oscillating in a periodic manner between these states, okay. You can relate to biological processes there, okay. So is that clear? Yeah. I'm sorry?
So do the number of attractors and the stability of the attractors, would they depend on the network topology?
Yes. Can we take this question in the end, Soling, because I can give you results, okay. And Kaufman's paper gave a result which subsequently has been found to be wrong, and then with a nuanced result you find various things. So I will not get in here, but I can give you some results on that, okay. So Kaufman already in the 1969 paper for random Boolean networks suggested a formula. So as the system size increases and as the connectivity increases, how many attractors you expect, okay. So let's not, if you can hang on to the end of the talk, you can ask me, okay. So, okay. So that's the case of deterministic dynamics which we obtained with the synchronous update, okay. Now of course, as my friend asked there, the timings of different processes are not similar, right, in biology. So, and we are making a fundamental or a simplistic assumption that there is a central clock in the case of the synchronous update. So of course, to circumvent this problem, one proposal which has been made is to go from synchronous to asynchronous update, which tries to make this process a bit more stochastic, and different nodes are updated at different time points, okay. And in the literature, starting with the work of René Thomas in 73, there are various versions of synchronous updates which have been proposed, and in the interest of time I am not going to go through them, but rather take the most widely used asynchronous update scheme, which is known as the fully asynchronous update scheme, to illustrate how dynamics can be different when you view it with synchronous update versus a asynchronous update. Okay. So for the next few slides, whenever I mention asynchronous update, I am going to take this fully asynchronous update scheme. The remaining things are, they are just incremental over the basic idea, not important to actually grasp the concepts. So let's look at the 5-node network which I have taken as example in the fully asynchronous case. In the fully asynchronous case, what happens is that at each time step, rather than updating all nodes, you randomly choose one node and update it, and the remaining nodes don't get updated by their states. Okay, and you can keep playing this for a long time and you get the state transition graph. So in this 5-node network, let's say at time t plus 1, we chose only randomly the gene x2 to be updated. So using the same update rule, by evaluating starting with all genes being at state 0, you can figure out that x2 will go to 1 at the next time step. However, the all other nodes remain in the same state. So in the synchronous update scheme, we went from all zeros to 0, 1, 1, 0, 0. So in this asynchronous update scheme, where in this instance we randomly chose x2 to be updated, we rather went to 0, 1, 0, 0, 0. Okay. So in the synchronous update scheme, if you think carefully, from a given state you can, depending on the choice of the node you update, you can go to different states. Okay. While in the asynchronous update scheme, in the synchronous update scheme there is only a unique successor state starting with a given state. So to explain better the difference between the asynchronous and synchronous dynamics, I will go away from the 5-node example, but actually take a simpler 3-node examples. Okay. And these motifs you have come across already in the talks by Mohit and others. Is there a question? No. Good. So I am going to take these two motifs which have been mentioned quite heavily during this workshop. So the first is a 3-gene motif, which is a positive feedback loop. Again, the 3 genes and the associated Boolean rules are written there. Okay. And this is a negative cycle, okay, with 3 genes again, and the Boolean rules are written. As already has been covered in this talk, the first is a positive feedback loop. You expect multi-stability. In the second case, you expect sustained oscillations. Okay. So let's take the synchronous update for these 2 3-gene networks and figure out the state transition graph. So the state transition graph is going to be very simple to figure out. There are 3 genes, so 2 to the power 3, 8 states. Okay. For each of the 8 states, you figure out, starting from each state, which is the next state you flow into, and you make that directed graph. Okay. Here, because there are 3 states, I didn't write the integer equivalent, I have written the states explicitly. Okay. So if you see, for the first case, you have 2 fixed points here. So if you start with 0, 0, 0, you remain in 0, 0, 0. You start with 1, 1, 1, you remain in 1, 1, 1, and there are 2 3 cycles which are shown here. Okay. That's the state transition graph. For the negative feedback loop, you get actually 2 attractors, both cycles, one a 2 cycle and second a 6 cycle. Is that clear? Now if you, rather than use the synchronous update, use the fully asynchronous scheme, the state transition graph will look more like this. The most important thing to realize is that in this case, if you start at a given state, there is only one unique state you flow to. In this case, from a given state, you can flow to many different states. Okay. Now the first question which must bother you is that even if we use the asynchronous update and create the state transition graph, how do we identify attractors in the asynchronous case, right? So mathematically, you can identify attractors in the asynchronous update scheme as follows. Yeah. It will become apparent. Okay. So these slides have been very carefully prepared, and maybe this is the right time to acknowledge that I didn't make the slides. My students made the slides. I don't make such efforts. Okay. So,
the asynchronous case, you'll be choosing nodes randomly, right? So by random, you mean you'll be choosing them through a probability distribution or something?
So I didn't go into the details. So there are various versions of asynchronous which I listed. In some versions you choose completely random. Some versions you have a deterministic order of random. That is, you can decide between the n nodes in some order they are updated.
Right. Okay.
All those variations have been studied in the literature, but they give you essentially the same result. So let's not
Just in this case, what are we doing?
I have taken randomly one. Okay, it's a fully asynchronous case. At each step, we chose randomly one node. Okay, that's the widely used thing. So I'm using that. Okay. Of course, these edges have been made, but there is a probability associated with each jump, which I am not showing there. Okay, for simplicity. So let's come back to the question: how do you identify the attractors in the state transition graph? Okay, which has been shown for the asynchronous update. So mathematically, what you have to do is you have to actually identify the strongly connected components in this directed graph, and those strongly connected components from where you cannot flow outside that strongly connected components happen to be the attractors of the asynchronous dynamics. So let me identify the strongly connected components here. So this is the state transition graph for the positive feedback loop of 3 nodes. So this is a strongly connected component, because if you are in 0 0 0, you can go back to 0 0 0. This is a strongly connected component 1 1 1, you remain here, and this is a 6 cycle or 6 cycle of 6 nodes, which is also a strongly connected component. Here there is only one strongly connected component of 6 nodes or 6 states, which is shown here. So these two are attractors, because from here you cannot flow outside the strongly connected component. But here, if you see, this strongly connected component is not an attractor, because you can go from here to here and here to here. Is that clear? You can go out of there. And in this case, this is a complex attractor, because in this strongly connected component, once you are here, you cannot go out. You can come from here to here, but not go from here to here or here to here. Is that clear? That's as simple as that. What you should realize is that in the synchronous case, a cycle is such that you visit the states of the cycle in a defined order. In the asynchronous case, for example, here with the 6 nodes, you can visit the 6 nodes in a different order, but you are locked in those 6 states. Okay. So one result I can give you straight away is that as far as fixed points are concerned, they are not dependent on the type of update. That is, the fixed points that you obtain with synchronous update, you will get the same with asynchronous update. And in most situations, while we are reconstructing and modeling, we are interested in fixed points. So the type of update may not be that relevant. It only matters if you are looking at complex attractors of this type. Right? There is a statement here I will try to omit now in this for the sake of time, but I will come to it later. So to summarize, between synchronous and asynchronous dynamics, in the synchronous case, we assume that all components take an equivalent amount of time for update. In asynchronous, of course, different components take different amount of time for update. In practice, here every node is updated at every time step. Here one randomly chosen node is updated at a given time step. Here the dynamics is deterministic, here it is stochastic. And more importantly, as I emphasized, in the state transition graph, there is only one successor of a given state in the synchronous case, while there could be multiple successors in the asynchronous case. And Kaufman, throughout his work, majorly used the synchronous update scheme, and René Thomas, who first introduced, all his work typically used the asynchronous update scheme. I was contemplating if I should cover this topic or not, but in the next few slides I will cover a slightly advanced topic which might be interesting from those who want to maybe work on this area. So if you look at the types of attractor in the synchronous dynamics, there are essentially 2 types of attractors that you saw. One fixed points, the other cycles. These are simple loops because you have a defined order in which you will visit them. However, in the asynchronous case, the types of attractors are of 3 types. One, fixed attractors. So whatever is fixed point in synchronous will also be fixed point in asynchronous. So there is no difference here. But in terms of other types of attractors, there is a complex attractor. Example I showed in the previous case of the 3 node negative feedback, and also a simple loop. And the attractors in the synchronous case can be broadly classified into what Clem and Bornhold have called stable and unstable. Maybe somebody asked a question, so I'll cover that here. So, by stable and unstable, maybe that's not the right type of vocabulary to choose. This classification was proposed in 2006. So, broadly, without looking at the slide, some of the attractors that we obtain maybe with the synchronous update may be artifacts of the synchronous scheme. That is, if you introduce a small amount of noise, say with time delay, they may go away. And Bornhold and Clem have tried to characterize which of these attractors in the synchronous case are stable, that is, they are not artifacts of the updating scheme, and which are perhaps only artifacts of the updating scheme. So, what they proposed is a heuristic which is very involved. I will try to give you a feel of what they did to identify and classify attractors into stable and unstable case. So, what they did is that, this is the case of the 2 cycle in the 3 node negative feedback case. Okay. So, if you were to do the synchronous update, if you start at 0 1 0, in the next time step you will go to 1 0 1. Okay. So, what Bornhold and Clem do is that they introduce a small perturbation associated with it, which is basically a time delay in the update of a given node. So, say you delay the update of node B, this is like the asynchronous update. So, in the next time step, these 2 nodes get updated but not B. So, you see now you have gone from 0 1 0 to 1 1 1. This is not in the basin of attraction of this attractor. So, this attractor is not stable. So, actually you have to check through all combinations of nodes for delay and see if any combination takes it out of the basin to identify which are the unstable attractors. So, without going into the details, if you were to actually run the simulation and identify which of the attractors in the synchronous case are stable and unstable for these 2 examples, you will find that the fixed points here are stable. Actually, fixed points are always stable. There is a theorem for that. As far as these 3 cycles are concerned, they are actually unstable. And if you see in the corresponding asynchronous case, these 2 are clearly attractors, but there is no corresponding attractor in the asynchronous case for these 3 cycles. So, they are lost as unstable. In this case, again the 2 cycle is gone because it is unstable. The 6th cycle is actually stable, and you have a corresponding complex attractor of 6 states in the asynchronous case. Okay. Yeah. Ishitwar, go ahead.
So you have some set of rule of randomly selecting those nodes in asynchronous update. So is this because of that rule that the nodes that are in synchronous one are essentially showing some features in that asynchronous one?
Can you repeat the last part?
Oh, as in like, is it because of that rule that the stable nodes in the asynchronous update are again the attractors in asynchronous one, or is it like it does not depend on that rule, it just always be the case?
So I can't go into the details, but here's a mathematical theorem. So any fixed point that you obtain remains a fixed point in both synchronous and asynchronous case, and it's also stable for this time delay. Now, the stability or instability is only a question for cycles, that is anything which is 2 or more nodes or states which are cycling in the synchronous case. There are certain cycles which turn out to be unstable, because if you introduce a small time delay, they go out of the basin. Okay. And those will not be found in the asynchronous case, because in asynchronous case we are not updating in the same order at every time. So there is no analytical proof as far as I have found, but the things which are unstable here, they won't be found here. Things which are stable here, they will have correspondence in the asynchronous case. Okay. I don't think there is a mathematical or analytical proof for this, but this is just an observation that one has made.
I just want to know if I got it right. So in the unstable case, so if you introduce any perturbation such as the delay you mentioned, you can go from that cycle to say another cycle, right? So for example, in that case,
so this is unstable in the sense that it is no longer a attractor.
Yeah.
You are interested in the attractor or steady states.
Right.
So what I am trying to say is, so what I am trying to omit is that if you run the equivalent differential equation based dynamics of for this negative feedback loop, you would actually get the result in continuous dynamics which is corresponding to this 6 cycle. You will, in the continuous case, you don't have any correspondence for this 2 cycle. So by actually eliminating these artifacts of synchronous updates, you can identify which of the attractors you obtain in the synchronous case that may have direct correspondence in the continuum case as well. Okay. So maybe let me avoid that. Okay. So I wanted to bring that in, but I thought it was too much to bring in the talk. Okay. So so till now I have 15 more minutes, so I don't think I can cover everything. So we have made a case for studying the GRN dynamics. I have introduced the basics of Boolean network modeling, and I have shown you the differences between the dynamics that you obtained under the synchronous and the asynchronous update. Okay. I don't think I will be able to cover the last part. I will only be able to cover this most likely, which is types and choices of Boolean functions. Okay. So I am switching gears and coming back to some historical events in the area of life sciences over the last say 200 odd years, to make a case why Kaufman made choices in 1969 which he had no other options out there for. So if you look at it, Darwin proposed his theory of evolution in 1859, Mendel's work in 1865, then 100 years to central dogma. Subsequent and around that time, Monod and Jacob worked out the regulation of lac operon, and Gordon's experiment was also around that time. However, unlike the post-genome era that we are today, we did not have those high throughput experiments like ChIP-seq to figure out which transcription factor binds to where all in the genome, which can give you directly the directed network of transcriptional regulatory network in a given cell type or whatever, even in single cell organisms. So Kaufman did not have the choice of the availability of data for the directed network of interactions which he was modeling for. Furthermore, there may not be enough experimental data to even assign the functions at each node for combinatorial regulation. So he was actually way ahead of his time, Kaufman and others, because they had the foresight to think that we should view this gene regulatory network as a dynamical system and the steady state attractors as different cell fates. Okay. So they made a leap of faith at that time in the pre-genome era. So to make the point explicit, in this pre-genomic era, Kaufman and others heavily studied these random Boolean networks. And what were these random Boolean networks? And Soling was asking a question. I won't go into the details of that because today it is unclear to me if it is relevant to continue studying them. But to recall, what Kaufman did was that since he had no knowledge on the structure of these gene regulatory networks, so he chose n nodes or n genes and connected them randomly such that there was a fixed in degree for each node. That is, he chose also let's say k fixed links or fixed genes in the model which will regulate a given gene. So these were known as the NK networks as well. Further, of course, there was no information on the let alone already you did not know the interaction, so there was hardly any information on the regulation of those genes. So he chose randomly some function at each node given the inputs amongst all possible Boolean functions. So these were the random Boolean networks which he used to infer the dynamics of real gene regulatory networks. And for most of the last century, since the proposition by Kaufman and Thoma, people studied heavily, even in physics, the properties of these random Boolean networks. But in the post-genome era, things have changed. In the last 20 years or so, we have sequence genomes. The sequence genomes gives you the parts list, which gives you the different components of a given organism, and you can identify the important components to construct a model for a biological process of interest which you would like to model. Subsequently, we also have information on the who regulates whom. For example, through high throughput ChIP-seq data, you can figure out which transcription factors control a given gene. Further experiments such as knockout or overexpression assays can tell you or give you a hint on what is the logical update rule or the combinatorial regulation at a given gene, through also combining with expression data sets, for example, RNA-seq, single cell RNA-seq, and so on. And furthermore, those data sets also tell us the steady state expression patterns associated with different cell fates and so on. So what has happened in the last 20-25 years or so is that availability of this information has led to construction of real models, in the sense that they have actual genes and connections, okay, and update rules associated with a given biological process. And to date, there are also now repositories which sort of document these different published models. A recent paper actually has documented more than 230 such models which have been built for different biological processes, starting from say cell cycle to cell differentiation to cancer. And these models also span the organisms across the kingdoms of life. Okay. So you actually have access to real data to or real models to now study the last 20 years. So it may not make sense now why I am making a case for this, but it will be more evident tomorrow when I analyze these corpus of models in a more detailed fashion. So one thing which is still a challenge while constructing such Boolean models is how to make or choose the right function at a given node. Say you know that this gene G is controlled by or regulated by 5 genes X1 to X5. Okay. What you need to realize is that the number of possible Boolean functions when a given gene is regulated by k other genes grows faster than exponential. For example, if you had only one gene regulating another gene, the number of possible genes for possible functions is only 4. If you had only 2 genes regulating another gene, the number of functions is 16. So actually the number of Boolean functions with k inputs is given by 2 to the power k. So basically this number is equal to that number when you insert the right k. So by the time you reach 5 genes, so a given gene is regulated by 5 other genes, the number of possibilities is more than a billion. So Kaufman was only studying networks with k equal to 2, but in real models you can very easily have k 4 or greater. So if you look at, for example, the ENCODE data, the chipset data for say HEK cell line or something, it's very easy to find in a given promoter more than 5 genes binding. So if you were to construct the gene regulatory network or the genome scale network, finding k greater than equal to 5 is very easy. But if you were to make a Boolean model, then for each node you have to choose which one of the billion functions is actually you should assign, and that's not an easy job. Okay. Already these simple models throw a challenge. So a question which arises is that there are more than 230 models which have been built, and many genes in these models which signify real biological processes. How have these reconstruction or modelers have assigned the function? It's highly unclear, but I will like to, rather than present my view of it, quote two of the authors or researchers who have extensively worked in the area. So these are 2 prominent reviews in the area. One by Rekha Albert, of course Albert and Barabasi. She has worked heavily in this area. So she says how, during the modeling or the reconstruction effort, how do you assign a function? When such information is not available, one can construct several variants of the Boolean rules and determine the one that best reproduces the known properties of the real system. Essentially, it's very obscure. Typically, they may have chosen something which best fits the experimental data. Kessler in this review says that typically an expert extracts natural language statements that explain specific interactions from literature, which are then manually transferred to Boolean functions. So it's basically the interpretation made by the modeler of the experiment which best fits the data. In the absence of the information, people have also tried workarounds. So this is a prominent paper which has been cited a lot by the group of Chow Tang, where they've used a Boolean model to simulate the yeast cell cycle network. Here actually, so many genes are controlled by more than one other gene. So rather than choosing a actual Boolean function, they use a threshold function. A similar function was also used by the Mohit in his work, which he presented in the small cell lung cancer model, where he actually doesn't choose a function, but he chooses this threshold function, which is more like a majority rule. So then you don't have to go through the billion possibilities to find one. So one of the biggest drawbacks of choosing a threshold function is the following. In real biological systems, we know that many promoters have a veto kind of a regulation. That is, there is one global regulator which is sitting there where RNA polymerase should sit, and regardless of what, if other regulators are expressed or not, this gene will not be expressed until that regulator is off. Such type of veto regulation is not captured by these threshold functions. But in the limitation of the data, people have used threshold functions for modeling as well. But you should remember, and also Marcin in his work with Olivier in a paper in 2012 in PNAS 11, he has actually delved in depth of what are the limitations of choosing such functions. So I won't use threshold functions, so I would ask the following question that are there then certain types of functions we can limit ourselves to which are biologically meaningful rather than looking at all the huge possibilities 2 to the power 2 to the power k while modeling and reconstruction efforts in Boolean model. So how am I doing with time? Okay. So I will not be able to do the last point. So I'll introduce 4 or 5 classes of functions which can be considered as biologically meaningful, and you will understand better in tomorrow's talk why I am introducing this type of functions. So these functions capture certain properties which are associated with real biological systems. So the first kind of function which I will introduce is what is known as a effective function. So let's take a 3 input function. So the gene F is controlled by 3 other genes x1, x2 and x3, and effective function, I mean this is already defined mathematically in computer science literature already for ages. I am not giving you the mathematical definition, but actually trying to give you intuition through this slide what an effective function is. An effective function is one where each of the inputs is effective. And how do you decide an input to be effective? So let's say you want to decide if x1 is effective or not in this function whose truth table is shown here. So then you fix x3 and x2 to a fixed state. So let's say you fix x3 and x2 to 0 and 1 and then change the value of x1. So here we change the value of x1 to 0 and 1. In at least one such combination, the change in value of x1 should lead to a change in the output value. Okay. Unless that happens, then this regulator has no effect on the gene that is regulating. So a function is effective only when all the inputs are effective. Clear? And of course, biologically there is no point in choosing functions which are ineffective. Okay. So ideally we would like to limit ourselves to our choice to effective functions. A second property and a class of functions I would like to introduce is what are known as unate functions. These capture the property of monotonicity associated with many regulatory effects. So say for example, you have a gene F which we know is regulated by 3 genes x1, x2 and x3. Somebody asked the question, so now I am making it explicit. So from biological literature we also know that x1 and x2 activate F while x3 represses F. Okay. Now you should choose a function which aligns with this experimental fact as well, that is x1 and x2 should activate, x3 should inhibit. You can ensure this property of activation and inhibition associated with each regulator by assigning positive or negative uniqueness with each input. So here I will try to show you how you choose a function which allows that for x1. So x1 is supposed to activate F. Okay. So there is a mathematical definition of unate function. I am omitting it. I am trying to give you a feel of how to what such functions do. So then we fix x3 and x2. After fixing x3 and x2, you should see through the truth table that whenever x1 increases, that is x1 goes from 0 to 1, there should be at least one case that the output value should also increase so that it activates. And in other cases it may not change, but it should not be the opposite as well. It should not reduce. Okay. So you can do this check for each input. So if you have an activator, you want positive unit. If you have an inhibitor, you should have a negative unit. In the negative unit case, you should go down. Okay. And a subset of functions satisfy this unate property. And so essentially if you know these links, you can impose the uniqueness for each input and choose functions from the set of unit functions which comply with the activation and animation. Yes.
I had a query about the effective function. So, as we see in this case, the function is effective, but so in this case, it's like 25% of the cases it turns out to change the input. Say it's even lower. So, should we even use a function which is effective, but like say in 10% of the cases only it's making a change? So, are they even useful?
Let's not ask the question. So let's invert the constraint as follows. You would want effective function. What you want additionally, which class of functions are achieving that, I will come slowly. Okay. Effective may not be just enough. Okay. Effective is not unit. You may want unit as well. Okay. But unit may not be all everything to it. Okay. So is the part about uniqueness clear? So the subsequent class of functions I would like to introduce is what are known as canalizing functions. So these were introduced by Stuart Kauffman in his book in 1993. So the property of canalization is as follows. A canalizing function is one where at least one of the inputs is canalizing. Okay. And what is canalizing? So look at this truth table associated with this function. X3 is canalizing because if you choose one of the input values for X3, here in the case 1, regardless of the state of X2 and X1, the output is fixed. Okay. So this can actually do the veto type of property. Okay. Fine. So this is the set of canalizing functions, and Kauffman proposed in his book this class of functions as possibly ones which nature may prefer, in his words. He hypothesized that way. See, the property of canalization, which is associated with a given input, can also be extended to a class of functions, a subset of functions which are known as nested canalizing functions, where each input is actually canalizing in a hierarchical fashion. So let me take an example of canalizing function, nested canalizing function. So here, once you choose the output value of X3 to be 0, regardless of the state of X2 and X1, you have output as 0. If you choose X3 as 1, but then choose X2 as 0, regardless of the value of the X1, the output value of the F is fixed, and similarly for the third one. So all inputs are canalizing in a hierarchical fashion. There are many properties, mathematical properties associated with this canalizing function, nested canalizing and canalizing functions, which we have found, and we have proofs for that. I am omitting here for simplicity. So so if you choose or limit yourself to these classes of functions, how does the space of functions look like? How do they occupy, what space of or subspace of functions they occupy? So this is easy to see or view them by looking at all possible 4 input functions. So 2 to the power 2 to the power 4, there are 65,536 functions. So let me take this rectangle as the complete space of 65,536 functions. So I mentioned this bias. Okay. So half of the functions will have odd bias, that is bias between biases 0, 2, 4 to 16, and half of the functions will have even bias. It's easy to prove. Very few functions are ineffective, and we have a mathematical proof that if your bias is odd, you can only be effective. So that is, any ineffective function will only have even bias, and when you have an odd bias, you are always effective. We have a proof for that. If you look at canalizing functions, they occupy space in both even and odd bias, more in towards the odd bias functions. And this is a schematic cartoon. The shapes should not be taken that seriously. It's drawn to some proportion. The unit functions also occupy both even and odd functions space. Some of the canalizing and unit functions can be also ineffective, because one input can be canalizing while another input can be ineffective. Okay. While the nested canalizing functions occupy this small space in the odd bias case. I didn't have the plot here. What I can show is that as k increases, the set of nested canalizing functions occupy a minimal, very small space of the total space. That is, the fraction of functions at k equal to 5 which are nested canalizing is a very small number. Okay. So it may be much more easy to handle that space, if I may say so. So I think I don't have time. So I'll skip the last part, how do you incorporate landscapes in Boolean dynamics. I'll cover that as part of our research and go directly to my concluding slides. So of course Boolean network is an oversimplification. There are several limitations, but I would argue that it's an attractive approach. It is simple, elegant and perhaps powerful, provided you have the clear question in mind to address. And in this context you may want to also think of these quotations by Karl Popper, where he says that science may be described as the art of systematic oversimplification. And George Box said that essentially all models are wrong, but some are useful. If you want to read how Boolean models can be useful while modeling large-scale gene networks, this is an excellent perspective by Stephen Bornhold in Science in 2006, where he argues that less is more in modeling gene regulatory networks. For those who are interested in getting into the area, of course the book by Kaufman is a must read for anybody who wants to work on complex adaptive systems, complex systems from a biological perspective. Here are some reviews I would like to recommend, which we actually used to prepare this talk. This review is very important if you want to see the historical developments by various pioneers in the Boolean modeling literature. If you want to see these classes of functions, I refer to our paper in Nexus. And I didn't cover this, but this is where we develop the framework to incorporate landscape within Boolean modeling. With that, I'll end by acknowledging the three people actually who made the slides. I just told them the idea. There was a lot of effort to these transitions. So my students Madhumita, Priyatosh and Ajay, they worked really hard for the last 2 weeks to make these slides. It's easier to give a research talk than pedagogical talk. And I acknowledge various funding agencies which has supported me during my decade in math science. And thanks Citabro for the opportunity, and I'll be happy to take any questions.
Maybe a quick question.
I don't want to stand between lunch and.
That's why I said quick question.
Yes.
So, I mean, in this context of like Boolean networks and Boolean neural networks, I mean, so in this framework, does it allow us to say anything about the edges, or is that always coming purely from experimental? Like, can I make some statements that maybe this edge needs to be there? Can it make a prediction that, or is that purely experimental? The edges.
Very good. So we have not delved into the reconstruction effort per se so far, but say you have a bunch of facts, okay, a bunch of components, bunch of information of which interactions you known from literature, and you want to assemble a simple Boolean model to capture, let's say, 2 cell phenotypes, say 2 differentiated sets, okay. Typically when you go about building that, you may encounter that the existing network is non-compliant with the experimental observations. So then you may have to either remove an edge or add an edge, okay. And so you can think of kind of Monte Carlo sampling kind of methods to see which are the edges which are best fitting the data and so on, okay. So I think people have done, and I will try to show you an example of one system which has been modeled by a prominent group over a period of 15 years, the root stem cell niche tomorrow. They have built, 5 or 6 models over the ages, and I will try to see if, as they have made the model more complex and more detailed, have they, are they still compliant with the basic, aspects of the landscape, which you expect of the developmental process they are modeling tomorrow. Okay, for sure, yeah, it can guide experiments for sure.
Thank you. Okay, so in view of the time, maybe we can thank Arjit once more and break for lunch. Couple of quick announcements.